So hello, and today we're simply going to be going over the homework for Chapter 18. I hope you all went and checked out the demo at the College Board's website on how to submit information. You're going to need to be able to do that. Like I said, unfortunately, one of the reasons I was delayed in doing this video today was the fact that it took me a lot longer to grade the homework than I expected, mainly because some of you have really scribbly handwriting. Don't do that on the AP exam. You need to make your final answers perfectly clear and not scribbling. These people are going to see hundreds of these tests, and you can take it for granted that if they're having trouble reading it, they won't bother. They'll just mark it wrong. So you need to make all your work clear. And yes, you need to show your work. You need to show where your answers are coming from. A whole lot of people got lost points because they weren't using the right numbers. You can get credit for using the right equation but having a wrong number. That might get you some points. But if you just give a numerical answer, it's either right or wrong. So they need to know where you are getting your answers from. In the same way, a lot of people lost points on the homework by just leaving stuff out. You can't leave stuff out. Everything that's part of the equation has to be part of the answer. You have to account and balance everything. Along the same lines, it's thermodynamics, which means, surprise, surprise, you have to put signs on everything. You can't just leave numbers. It is always important in thermodynamics that you indicate energy in or energy out. Positive potential, negative potential. Positive work, negative work. You have to indicate clearly any amount of energy, whether you're talking about it going in or coming out. So, on to the homework problems. Problem 22 is just balancing skeletal redox reactions. We've done it several times. The only difference is this one wants you to use a basic solution. And it says use the half reaction method. I don't care what method you do, as long as you get the equations balanced. Which does bring up a point. Several people lost points on this problem because they left stuff out. The ammonia is part of this equation. You can't leave it out, and you have to balance it along with everything else in the equation. Problem 32 gives us a galvanic cell of copper and silver with an outside power source available and asks which way the reaction is running. It's a galvanic cell by itself. Silver is the cathode, copper is the anode. The electrons are going from the copper to the silver ions. If the silver is getting produced, then the silver is the anode, the copper is the cathode. The electrons are going from the silver to the copper ions. The potential for the cell running as a galvanic is 0.46 volts. To make it run in reverse, you'd have to apply a potential of more than minus 0.46 volts. That is more larger negative value than that. Problem 36, we're again given a galvanic cell, this time of zinc and copper. The copper is being reduced, so it is the oxidizing agent. The zinc is being oxidized, so it's the reducing agent. And the electrons are going from zinc to the copper ions. The potential for the copper, plus 3.4 volts. The potential for the zinc, minus 0.76 volts, but it's running backwards, so it's positive 0.76 volts for 1.10 volts. The copper electrode should be getting heavier. The zinc should be getting lighter. Problem 44 asks you to look at two earlier problems and give the line notation for them. Problem 38 doesn't give any electrodes, so we're just going to have to say there's an anion to start with. Phase change, the iron plus 2 and iron plus 3 are in aqueous solution together. Hit the salt bridge. The iodate and the protons are in the same aqueous solution. The iodine would be a solid under these conditions. And that brings us to the cathode, whatever they're using as an inert electrode. In the B problem, zinc is the anode, zinc ions are in solution, the salt bridge, silver ions in solution, and zinc is the cathode, and silver is the cathode. In 42, they again didn't give us electrodes, so it would be something for an anode. The peroxide and protons would both be in aqueous solution. There's a change in phase. The oxygen would be as a gas. Salt bridge, again, the peroxide and protons would be together in solution, and finally we'd end up with whatever they had as a cathode. The manganese would be the anode. Vertical line, the manganese plus 2 is in solution. Double line for the salt bridge, the iron plus 3 is in solution, and the iron ends up being the cathode. The ions are all in aqueous solution. All the concentrations are 1 molar, but I left those details out so that the lines wouldn't be long and stretched out. If you were going to do just one long one, you'd have to note the concentrations, and you'd have to note that they were all aqueous solution. Problem 50 notes the 2 redox steps you have to go through to find out how much manganese there is in a piece of steel. First thing you have to do, of course, is you have to oxidize the manganese from solid to its plus 2 state in solution. That's a 6 electron transfer. The potential for the nitrate plus 96 volts. The manganese reduction potential, 1.18, negative 1.18, it's running backwards, so it becomes positive, so the potential is 2.14 volts. It's a 6 electron transfer, and so the delta G0 would be minus 1240 kilojoules. We then have to oxidize the manganese plus 2 all the way to permanganate using periodate. The permanganate's reduction potential, 1.51 volts, but it's running backwards, so that becomes minus 1.51 volts. So the cell's potential is 0.09 volts. It's a 10 electron transfer, a Faraday, 0.09, and we find out that the delta G0 is minus 87 kilojoules. Problem 62 gives us a variety of molecules and ions and atoms to consider for redox potentials. The one with the most positive reduction potential is the bromine, so it would be the best oxidizing agent. Calcium has the worst of the reduction potential, so it would be the best reducing agent. Permanganate at 1.51 will be able to oxidize anything with a worse reduction potential, which is, of course, the hydrogen, the calcium, the cadmium, and the bromide. You have to keep in mind, bromide's perfectly capable of giving away electrons and being oxidized. Many people left the bromide out. And finally, of course, for the last one, both the bromine and the protons are easily reduced. In problem 86, all the potentials has to come from the difference in concentration of the nickel ions, and therefore for A and E, where the concentrations are the same at 0, for B, 0.009 volts, for C, 0.03 volts, for D, 0.13 volts. For problem 76, you're given reduction potentials for both gold plus 3 and thallium plus 1. The gold is more positive, so it would run as written, 1.50. The thallium would be reversed, so plus 3.4. And so altogether, the potential would be 1.84 volts. Delta G0, it's a 3 electron transfer, obviously. A Faraday, 1.84. So the delta G0 would be minus 533 kilojoules. We have to put in the K, that's 10 to the 1.84 times 3 divided by 0.0591, 2.5 times 10 to the 93rd. And finally, potential for the cell with the given concentrations, 1.84, 0.0591 volts, 3 is still a 3 electron exchange. The gold is to the first power. The thallium is cubed. That gets us 10 to the minus 10th. And so 1.84 minus 0.0591 volts divided by 3 times minus 10 gives us a potential for the cell of 2.4 volts. Problem 84 presents 3 different disproportionation reactions. Copper 1 to forming copper solid and copper plus 2, iron plus 2 to form solid iron and iron plus 3, and finally chlorous acid decomposing to hypochlorous acid and chloric acid. For copper, you have to find the right 2 1-electron reductions. Copper plus 2 to copper plus 1 has a potential of 0.16 volts. Copper plus 1 electron to copper 0, 0.52 volts. The more positive one will run as written, the more negative, less positive one will run backwards. So the reaction should have a potential of 0.36 volts, so it should be spontaneous. It's a 1-electron transfer, 0.36 volts, so it should have a delta G0 of 34.7 kilojoules, which gives a K of 1.2 times 10 to the 6th. The iron plus 2 to iron has a potential of minus 0.47 volts. The iron plus 3 plus 1 electron to iron plus 2 has a potential of 0.77 volts. So that would be the one running forward. For the disproportionation, the reaction that runs forward is the minus 0.44 volts. So that would mean that the other one would have to run backwards for minus 0.77 volts. So the potential for the cell would be minus 1.21 volts, so it should not be spontaneous at room temperature. The delta G would be positive 233 kilojoules per mole, and the K would be 1.2 times 10 to the minus 41st. And finally, the chlorous acid. The chlorous acid being reduced to perchlorous acid has a potential of 1.65 is running forward. The chlorate being reduced would be running backwards. And so the potential for the cell would be plus 0.44 volts. So it would also be spontaneous. It's a 2-electron transfer, 0.44 volts. So it has a delta G0 of 84.9 kilojoules. And that gives us an equilibrium value of 7.6 times 10 to the 14th. And finally, of course, we're reducing M plus 3, whatever it is, to metallic M. We have 0.56 coulombs per second flowing into the cell. It's flowing for 1,397 seconds. So we're getting 9,080.5 coulombs. 9,080.5 coulombs divided by 96,485 is Faradays. It takes 3 Faradays to produce 1 mole of M. So we're producing 0.03137 moles of M. It has a mass of 1.47 grams, so it should have an atomic weight of 44.9, and that means it's scandium. And that brings us to the end for today. I'll post a review sheet for the class tomorrow on Net Classrooms to help you just study up in advance. But like I said, you should have by now, hopefully, taken the test and sent it back in. And I'll have to see what the scoring is on those. Like I said, my basic plan at the moment is, if you are happy with your grade after the 2 tests and all the homework, because I'll post a grade for you later this week once I've graded all the exams, if you're happy with that grade for the course, you don't need to take the final. If you're not happy and want to take a final, try and raise your grade, then you specifically have to tell me you want to take a final, because otherwise I'm not going to bother making one up. Okay, and we'll see you again later.